Hi everyone, welcome back to Dave's Math channel. I decided to do a follow-up to the video I made yesterday on integration by partial fractions because these can get pretty complicated, and I'm going to give you a pretty complicated example today. It's going to be an example where we have to use Formula 5, it turns out. Anyway, let's begin. Here's the integral I want to try to solve. Suppose we're given the integral of dx over x cubed minus 8. We're asked to evaluate this indefinite integral. So how do we do it? Well, the first thing we do is we factor the denominator. That's always what we do. So if you factor x cubed minus 8 over the real numbers, you get x minus 2 times x squared plus 2x plus 4. So you're going to have 1 over x cubed minus 8 equals 1 over x minus 2 times x squared plus 2x plus 4, which we can write as a over x minus 2 plus bx plus c over x squared minus 2x plus 4. This is just a special case of Formula 5 here. Anyway, so that's what we're doing. And now we want to solve for these constants a, b, and c. So we do it the same way we did the last two examples, which I gave you in the last video. We just multiply everything by the common denominator, which in this case is x minus 2 times x squared plus 2x plus 4. That yields 1 on the left, and it yields a times x squared plus 2x plus 4 times plus b times bx plus c times x minus 2. And when we simplify all this, I'm not going to go through all the steps here, but you'll get something, you get a plus b times x squared plus 2a minus 2b plus c times x plus 4a minus 2c. And now we just identify like terms on both sides of this equation. So we start with a quadratic term. The quadratic term is a plus b on the right, and that equals 0 because there's no quadratic term on the left. And similarly, the linear term is 2a minus 2b plus c, and that equals 0 because there's no linear term. And finally, the constant term is 4a minus 2c, and that equals 1 because that's a constant term on the left. So we have this system of three equations, three simultaneous linear equations, and three unknowns. It's a pretty easy system to solve. The first equation gives you b equals minus a. When you plug that into the second equation, you get c equals what is it? C equals minus 4a. And finally, the third equation is going to give us 12a equals 1. We've expressed everything in terms of a. So a is 1/12. And then if you just plug in the expressions we got for b and c in terms of a, you see b equals minus 1/12 and c equals minus 1/3. So the end result is 1 over x cubed minus a equals 1/12 times the quantity 1 over x minus 2 minus x plus 4 over x squared plus 2x plus 4. That is the partial fraction expansion of the integrand. So now we can rewrite the integral just using this partial fraction expansion. We get the I equals 1/12 times the quantity, the integral of dx over x minus 2 minus the integral of x plus 4 dx over x squared plus 2x plus 4. The first integral here is easy. That's just the natural logarithm of the absolute value of x minus 2. And the second one I'm calling j. We have to do more work to evaluate that. So let's evaluate j. J is our new integral. J is the integral of x plus 4 over x squared plus 2x plus 4. How do we evaluate that? Well, you can use a little trick here. Remember the d cabin over cabin rule I went over a couple of weekends, a few days ago. In this case, we'll let cabin be x squared plus 2x plus 4. So d cabin is going to be 2x plus 2, or if you like, 2 times x plus 1. So we really just get 1/2 times the integral of d cabin over cabin, which is really just the integral of x plus 1 dx over x squared plus 2x plus 4, but then we're left with 3 times the integral of dx over x squared plus 2x plus 4, and I rewrote it here. I rewrote it as dx over x plus 1 quantity squared plus 1. And I skipped a few steps here, but we can evaluate this integral on the right using substitution first. So first we let u equal x plus 1. You'll get the integral of dx over du over u squared plus 3. You may recognize that as a special form of the arctangent. Remember, we had the integral of dx over a squared plus x squared equals 1 over a times arctangent of x over a. In this case, a is square root of 3, so we're going to get 1 over square root of 3 times the arctangent of u over square root of 3, but u is x plus 1, so we really, for the integral, we get 1 over square root of 3 times arctangent of x plus 1 over square root of 3, but we have to multiply the whole thing by 3, and 3 over square root of 3 is just square root of 3, so that's what's going to, that'll give us our second term, square root of 3 times the arctangent of x plus 1 over square root of 3. If I did that too fast, you should do it yourself. I mean, it's a lot of steps, but anyway, just try it yourself. I don't think it's complicated. First thing you have to do is a simple substitution. U equals x squared, x plus 1, and then you just use the rule for the arctangent. Anyway, that's what you get. So now we're almost done. We have an expression for j. We just evaluated this integral j, but we're not quite done because we still have to plug it into the expression we have for I. That's the integral we want. So we just do that. This time, at this point, it's just algebra. So we get y equals 1/12 times the natural logarithm of absolute value of x minus 2 minus j, but we already know what j is, so let's plug it in. So we're going to get 1/12 times the absolute natural logarithm of the absolute value of x minus 2 minus the natural logarithm of x squared plus 2x plus 4 over 2. That's just the negative of the first term we evaluated for j. And now we have to subtract the second term, which is minus square root of 3, times the arctangent of x plus 1 over square root of 3. And we're just left with an integration constant. So we could leave it like this, but we can actually simplify it a little bit more. I like to do this. Whenever you have a bunch of natural logarithms in an expression, you can just use properties of the natural logarithm. So you can combine terms. I mean, we can make the constant factor outside 1/24th and just multiply both of these all these terms by 2. That's going to give us 2 natural log of absolute value of x minus 2 minus the natural log of x squared plus 2x plus 4. But 2 times natural log of absolute value of x plus minus 2 is just natural log of x minus 2 quantity squared. And we're subtracting the natural log of x squared plus 2x plus 4. That's the same as dividing it inside the logarithm. So when we're done with all that, our first term is going to be the natural logarithm of x minus 2 quantity squared. We no longer need an absolute value because we're squaring something, and we know the square of anything is positive, or at least it's not negative. And then the denominator, this other term is also always positive, so we don't need an absolute value around it. So that's the first term. And then the second term is just what we had from the arctangent. We're just multiplying it by 2 because we divided the factor outside by 2. So anyway, that's the answer you get. That's probably the most simplified form of the answer that you can write down. And that's how you do that. So like I said, this was a complicated example. And you'll see a lot of complicated examples like this. These can get quite complicated, but I think they're always straightforward at least. I mean, we have all the tools we need to solve all of these different types of integrals of rational functions where we have to use integration by partial fractions. So it's a very powerful tool. It allows us to integrate pretty much any rational function expression. Anyway, so that's probably all I'm going to do on integration by partial fractions. I think we're done with all the sort of basic calculus. I'll probably make a few more videos where we actually apply calculus. Calculus has tons of applications in the sciences. And now that we know how to differentiate and integrate, we might as well put some of that to use. So the next few videos, I'm going to make a new sub-series on applications of first year calculus, and I think you'll enjoy some of those. So anyway, thank you for watching. Long live math, and I'll see you guys next time. Bye.